I am Ota Michihiro, leader of the Thermoelectrics and Thermal Management team. Our team conducts R&D on thermoelectric technology. The thermoelectric technology uses specific semiconductors to enable interconversion of heat and electricity. This lets us convert temperature differences into electricity or use electricity to control temperature. Thermoelectric conversion is not a widely known technology, but for example, it is used as an important power source for space probes. But due to its relatively low conversion efficiency, we rarely use it in our daily lives. Our goal is to make the thermoelectric technology used in space missions available for consumer use. We study materials, build modules, demonstrate power generation, and develop measurement techniques. Take a look at some of our main work.
Let's see how power is actually generated by a thermoelectric module. When you place your hand on the module, electricity is generated from the difference in your body temperature and the room temperature, which leads to rotation of the fan. Using one of the thermoelectric semiconductors we focus on, lead telluride, as an example, we'll show you the production process from materials to modules. First, raw materials, such as tellurium and lead, are placed inside a quartz tube. Then, the air is removed from the quartz tube to create a vacuum inside. The open end of the quartz tube is sealed by heating it up with a gas torch. We place the tube in an electric furnace and heat it up to over 1,000 degrees Celsius. With that, the material melts and undergoes a reaction to form a chemical compound. Next, high temperatures and pressure are applied to consolidate the powder of this chemical compound to make the elements for the module. Precise control of the temperature and pressure is the key to achieve high performance. This is how we make lead telluride-based thermoelectric semiconductors. Lead telluride can be doped to make N-type and P-type semiconductors depending on the dopants. The N-type and P-type lead tellurides are cut into columns and are aligned alternatingly. As you can see, the electrodes are connected to create a series circuit. By sandwiching them between two substrate layers, the thermoelectric module is fully assembled. We then heat the top and cool the bottom of the module to create a temperature difference. Electrons and holes flow from the hot to the cold side of the module. This flow of charge carriers draws the electrical current outside the module.
The conversion efficiency of this thermoelectric module is 12%, which is among the highest in the world. We create 3D nanostructures with sizes between 5 nanometer to hundreds of nanometer by precisely controlling the synthesis conditions for lead telluride. These nanostructures act as barriers to the heat flow, but the electrons can easily pass through. In this way, a large amount of current can be drawn by maintaining the necessary temperature gradient. We have also achieved good electrical and thermal contacts between the nanostructured material and various interfaces through our advanced electrode formation technology. Finally, we have devised various module configurations to leverage the temperature gradient, such as stacking of high temperature and low temperature modules. By optimizing the material, electrodes, and module configuration, we have succeeded in doubling the conversion efficiency compared to the conventional modules.
By combining various technologies, conversion efficiencies among the highest in the world have been achieved. For us, everything starts with craftsmanship. We make many module prototypes, and it's a process of trial and error to make the ideal module for each temperature and purpose. Take, for instance, this conducting polymer thermoelectric material. We drop a solution containing polymer onto a substrate. and remove the water through evaporation. It's an incredibly simple method, but it can make a module attachable anywhere. Different materials are used for different temperatures. Lead telluride for high temperatures, and conductive polymers for low temperatures. We are also developing new materials mainly composed of abundant elements such as sulfur and magnesium. We are also developing technologies to analyze thermoelectric modules. This is an X-ray CT. It operates via the same principle as a medical CT and allows us to perform non-destructive 3D observation of a module's interior. This is a cutting-edge electron microscope. It is used to observe a material's microstructure and composition in great detail. The gained knowledge is highly beneficial for improving modules.
Our research group is one of the few in the world that covers the whole range of thermoelectric research, from material development to module construction and analysis. We are a world leader in matching scientific discoveries with industrial needs to socially implement thermoelectric devices.
The precise assessment of the conversion efficiency of thermoelectric modules is among our top priorities. So far, there is no international standard. Different labs have different methods of measuring conversion efficiency. Up to now, there is no standard reference module that can be used to determine the reliability of equipment used to test modules. So we developed a highly durable reference module made of nickel alloys. Its properties remain unchanged even after lengthy and repeated use. To assess performance reliably, we need this kind of module as a standard.
We are collaborating with laboratories worldwide in an effort to advance measurement techniques in an international framework. Precise measurement techniques are a prerequisite for a fair and equitable market.
You may be wondering why there is a need for researching thermoelectric technology. If we take a look around us, we can see many instances in which heat is emitted unused into the environment, such as factories, computers, and automobiles. This wasted heat can amount to 60% of the primary energy supply in our daily life. If we are able to gather a portion of this heat as usable electricity, a huge amount of energy could be provided. Our bodies also produce heat. Thermoelectric technology could be used as a power supply for wearable devices. Thermoelectric technology is an old yet new technology that can help reduce CO2 emissions and conserve energy.
The conversion efficiency of thermoelectric modules has surpassed 10%. Like photovoltaic power generation, it's now closer to widespread use. For further information, please contact us. Our research team is eager to hear from you.